Welcome back. In this video, we're going to take a look at polynomial graphs, how we describe them, and how we can write equations of them given the graph. In our first example here, we have a cubic polynomial. It's a third-degree polynomial. We know that because it has two turning points. And we have three single roots. So when we report a polynomial graph, or when we investigate, we're going to describe by its degree, turning points, its roots, the type of roots. They're single roots because the graph crosses the x-axis at these points. And then we describe end behavior as x goes far out on the positive infinity. What does y do? As x goes far out on the negative infinity, what does y do? And then once we know the roots, we can write out our intercept form of the graph. Now let's take a look at another idea before we look at our next polynomial graph. We have this thing in algebra called the fundamental theorem of algebra that states a polynomial with degree n has exactly n complex roots, provided that roots with multiplicities are counted as single roots. So what that means to us is that whatever the degree of the polynomial is, we should have that many complex roots. So if it's a degree 3, we should have 3 complex roots, which include real roots and imaginary roots, which we'll talk later about imaginary roots. If it's a degree 4, we should have 4 complex roots, and they can be real roots or complex roots, or imaginary roots, I should say. So let's take a look at how we use this in the next graph. So here we have another third-degree polynomial. It's a cubic, it's got 2 turning points, but here we've got a single root because it crosses the x-axis, and then we have another root, but at the root it's a turning point. So we call this root a double root. So even though there are 2 real zeros here, this is what we call the multiplicity. Since the turning point happens right on the x-axis, and it's a third-degree polynomial, the fundamental theorem of algebra says that we have exactly 3 complex roots, as long as we count multiplicities as single roots. So we have one single root, and we have a double root here. So 1 plus 2 is 3. So we have 3 roots. It's just that this one right here counts as 2. Now, we write it out as one single root, one double root. We still have the same end behavior. And then we write it out this way. Now, that's not quite in standard form because we usually do this in descending order. So it would look like this. X minus 2, quantity squared, x plus 3. And the double root is indicated by the squared because that's where it touches the x-axis. Let's take a look at another example. Here we have a third-degree polynomial, but this time it only hits in one spot. We've got 2 turning points. We have one real zero, meaning one real x-intercept, but based on the fundamental theorem of algebra, we count this as a triple root since it is a third-degree polynomial. So it's just in the name, and it's in how we write the equation. So it's a triple root, even though it hits this in one spot, it's right at its turning point. Now let's take a look at a couple of graphs and their turning points and their roots and see how we write the equations. Here we have a cubic. We have a cubic that has a single root here and a double root here. So we have 3 roots altogether, because if we were to expand this out, we're going to have a cubic polynomial. And the way we write it is we take this root, it's to the second power, and then this single root is just to the first power. Now this crazy thing, we have a degree 7 polynomial. I know that because I've got 1, 2, 3, 4, 5, 6 turning points. So remember we said that the turning points will always be at least one less than the degree of the polynomial. And if I count up all the powers of x, I can verify that. So there's x cubed, x squared, x to the first, x to the first, so there's going to be 7 powers of x eventually. So watch how we write this. Here's a triple root, here's a double root, and here are 2 single roots. So we write x plus 3 cubed, x minus 2 squared, x minus 4 for the single, x minus 6 for the single. Now we'll take a look at complex roots that involve imaginary numbers later on in class, but this is just an overview and general idea of how we can write equations to polynomials given the graph. I hope you find this helpful, and if you have further questions, please ask in class or come in before or after school. Until next time, bye-bye.